Good afternoon. We are going to be taking notes on section 6.2, which is kites and trapezoids. All right, first thing we're going to do is start with the definition of a kite. A kite is a quadrilateral, so four-sided figure with two pairs of congruent adjacent sides, but opposite sides, put an S in there for sides, opposite sides are not congruent. So this is a kite, and you have two short sides that are congruent and next to each other, or adjacent, and then you have two long sides that are congruent and adjacent, but notice the small and the long that are across from each other are not congruent. So that is a kite. Okay, theorem. The theorem says that the diagonals of a kite are perpendicular. So if we use a ruler, we have a kite. Remember that your diagonals go from vertex to vertex, but non-consecutive, so not next to each other. And even just using a ruler, it's pretty obvious that it's definitely a 90-degree angle, which makes four really convenient right triangles. Okay, let's do an example on that. Kite ABCD has diagonals AC and BD. You can already tell that there are diagonals. What is the measure of angle BMC? So B to M to C is this one. And we've just learned that the diagonals are perpendicular, so that angle is 90 degrees. All right, our second question, what is the measure of angle ABM? Okay, so ABM is this little angle right up in there. And this is pretty easy to set up because we have a right triangle. And we actually do know that one of the acute angles is 35. So using triangle sum theorem, the 90 degrees plus 35 plus this little corner angle, I'm just going to call it angle B, adds up to 180. That's triangle sum theorem. There is your equation. So 90 plus 35 is 125. Plus angle B is 180 degrees. We're going to solve for B, so subtract 125 over to the right. And we get the measure of angle B equals 55 degrees. So this angle right there is 55 degrees. Okay, something else you need to know about the diagonals of a kite, and this is a corollary, it's an add-on. The diagonal that goes from the non-congruent vertex across to the other non-congruent vertex, here and here, that actually bisects the corner angles. So the diagonal between non-congruent angles bisects those angles. We're going to say those two angles. The diagonal between the non-congruent angles bisects. So these two are the same, and these two are the same. Does not work for the congruent angles. Speaking of which, something else that's true about a kite, and it's just a byproduct of the definition, is that when you have two congruent sides adjacent to two different congruent sides, the angles between the short and the long and the short and the long, those two angles are the same. So this again is a corollary or an add-on to the definition of a kite. It has one pair of congruent opposite angles. One pair of congruent opposite angles. And you can write in the rest of it if you want, but basically it's the angles in between the different sides. Those two are the same. So I wanted to make sure I added those on because they are on your assignment and they don't show up in your book, but they do show up on the worksheets. Okay, so number 3, what is the measure of angle BCM? So this is BCM right here. And this one's pretty easy to figure out because we know that this diagonal BD bisects B and D. So diagonal BD bisects angle B and angle D. And from that, we get that angle, the measure of angle CBM, has to equal 55 degrees as well. So if this is 55 degrees and that is 90 degrees, we can say by third angles theorem, third angles theorem says that if two angles of two triangles match, then their third angles must also match. So third angles theorem tells us that because both of them have a 55 degree and a 90, this little corner angle has to be 35 degrees. So the measure of angle MCB is equal to the measure of angle MAB, which is 35 degrees. Third angles theorem. All right, Roman numeral 2, trapezoid. Definition of a trapezoid is a quadrilateral with exactly one pair of parallel sides. And we know that the word exactly means one and only one. One and only one pair of parallel sides. So in this trapezoid, the parallels are obviously AB and CD. Now we're going to do a little body part labeling here. The bases of a trapezoid are the two parallel sides. So we usually refer to one of them as B sub 1 for base 1 and the other one as B sub 2 for base 2. Okay, legs. The legs of a trapezoid are the two non-parallel sides. The two non-parallel sides. So in this trapezoid, you have a leg on the right and a leg on the left. So two legs and two bases in a trapezoid. All right, flip the page. Okay, number 2, the definition of an isosceles trapezoid. Well, if you remember, isosceles triangle means two sides of the triangle are the same. In the case of a trapezoid, it is a trapezoid with congruent legs. So remember that in a trapezoid, you have one pair of parallel sides, and then the ones that are not parallel are the legs. So in this case, if it's isosceles, the left and the right leg are congruent. That's what makes it isosceles. Okay, number 3, definition of the median or the mid-segment of a trapezoid. You'll see both terms. Typically, you'll see mid-segment more often, though. All right, definition. The median of a trapezoid is the segment that joins the midpoints of the legs. The segment that joins the midpoints of the legs. So this point here is halfway up the left leg. This point here is halfway up the right leg. Notice the legs are not the same. So your mid segment is this piece right there. That's your mid segment. Now it just so happens that your mid segment is parallel to the other two sides of the trapezoid. So that's another characteristic, is the mid segment is parallel to the bases. And of course now we've got three parallel lines cut by a transversal on the left and a transversal on the right. And we can do all kinds of things with that. One of them are same side interior angles, like this one and this one, are supplementary. So all of our parallel line theorems apply to the mid-segment of a trapezoid. All right, really quick comparison with the median of a triangle. The median of a triangle, if you remember, goes from one vertex to the midpoint of one side. That's a median of a triangle. So a median or a mid-segment of a trapezoid goes from midpoint to midpoint. So it is different. All right, Roman numeral 3, trapezoid theorems. 6.4, given an isosceles trapezoid, the base angles are congruent. So we're shown here trapezoid ABXY with BX congruent to AY. That shouldn't be congruent. That should be parallel. So let's make that fix here. BX is parallel to AY. So let's mark BX and AY as parallel. And because this is an isosceles trapezoid, your legs are going to be the same. And this theorem, though, says that the base angles are congruent. Well, you actually have two pairs of base angles. You've got base angle A and Y. Those two are congruent to each other. And then you've got another pair of base angles, B and X, that are congruent to each other. So it really is two pairs of congruent angles. Now, what we kind of visited up there on the definition is that because you have two parallel lines cut by a transversal, X and Y are same side interior angles, which means that when you take X and Y, they are supplementary, which means they add up to 180 degrees. Same side interior angles are supplementary. That's going to be a really important piece of information later. All right, example 2. Draw one line on the isosceles trapezoid that defines a parallelogram. Draw another line or a different line that creates a different parallelogram. Well, if we were doing this in class, I would definitely have you work on this and come up with something. As it is, though, if you want a parallelogram to be parallel, in a trapezoid, we have one pair of parallel sides. So to make a parallelogram, I need the other pair of sides to be parallel. So I need to draw something that's parallel to that one, which would be a line like so. I can draw a different one going the other way. So if I want it to be a parallelogram, I need a left side that's parallel to this one. So if I draw it here, I now have a parallelogram. Opposite sides are congruent. When you draw this line to make a parallelogram, something nifty happens, which is that this creates an isosceles triangle. In other words, this side and that side are the same. Same here. Those two sides are congruent to each other. So that's kind of a neat little construction you're going to be working on later. All right, flip the page. Example 3. Draw two lines on the isosceles trapezoid that creates two congruent triangles. So you can only draw two lines. If you want to stop the video and see if you can come up with the two lines and then play it again, you can do that. So go ahead and pause the video and give it your best shot. Okay, coming back, there's actually 3 ways you could do this. You could drop perpendiculars, and that would create, and you're looking again for two congruent triangles. 1, 2. If you draw in the diagonals, the top and bottom triangles are not the same, but you end up with a left and a right triangle that are congruent. You also get a very large left triangle and right triangle that are congruent. So you actually get 2 different pairs of congruent triangles. The third one, let me draw a quick trapezoid here. And it's isosceles. So I try to make the legs the same. There we go. If you bisect one of the bases and draw in diagonals, then you end up with a left triangle and a right triangle that are congruent. So there's lots of ways to draw lines that create congruent triangles, which gives us many more opportunities for solving. All right, let's get into the theorems. Theorem 6.5 says that the diagonals of an isosceles trapezoid, isosceles in particular, are congruent. So if I take this trapezoid and I draw in a diagonal from A to C and a diagonal from B to D, this theorem says that AC is congruent to BD. This is only the case when it's isosceles. If it's not isosceles, the diagonals are not congruent. All right, theorem 6.6. A median or mid-segment of a trapezoid, and this is a little bit of a recap. They are parallel to the bases. So MN is a segment from the midpoint of the left leg to the midpoint of the right leg. So all 3 of these are parallel. And then here's the new part. The midsegment has a length that is the average of the bases. That's a really nifty formula. So MN is equal to 1/2 of the top base SR plus the bottom base PQ. That would be the average of the bases. So add them together and divide by 2. Okay, here's an example. A trapezoid ABCD and its median MN are shown. Find the value of X. Okay, so the formula from the theorem is that the midsegment MN is the average of the bases, so it's equal to 1/2 base AB plus base CD. That's our formula. So our equation that we're going to use this formula to build, MN has a length of 10, so 10 equals 1/2. AB is 2x minus 4 plus CD, which is x minus 3. That would be the equation you want to put a box around on your homework. All right, so first thing you probably would want to do when solving this is simplify inside the parentheses. So 2x plus 1x is 3x. Negative 4 minus 3 is negative 7. Now here's where I'm going to show you a nifty algebra move. To get rid of the fraction, rather than just create more fractions, we can use its reciprocal. We can multiply by 2 over 1 on both sides. This will cause the 2 on the 1/2 and the 2 over 1 to divide out. And on the left, we now have 20 equals. And now that the 2 is gone, there's no reason for that fraction to be there. So the 3x minus 7 is now out of the parentheses. See what a cool move that is? It gets rid of the fractions in one step and makes it a whole lot easier to solve. So I'm going to finish out here by solving with 3x on the right. So I'm going to add 7 over to the left. 27 equals 3x, and 3 times 9 is 27, so x equals 9. So remember that little algebra move. It will save you a whole lot of mess and effort. All right, we are at the end of the 6.2 notes. Have an excellent afternoon.